Welcome to week 6 problem. Let us begin with a quote by Feynman. The first principle is that you must not fool yourself. So whenever you are trying to learn some problems, try to understand the phenomena behind it. Question number 1. A particle of unit mass moves in a potential V of x is equal to ax square plus b by x square, where a and b are positive constants. The angular frequency of small oscillations about the minimum of the potential is. So for doing this problem, you have to understand that dV by dx equal to 0 at equilibrium point, as well as if you differentiate the potential once again, you get the spring constant k if you consider it as a linear harmonic oscillator. So V of x equal to ax square plus b by x square. So finding dV by dx, you get 2ax minus 2b by x cube. If x0 is the equilibrium point, we get x0 equal to b by a raised to 1 by 4. And if you differentiate potential once again, we get d square v by dx square is equal to 2a plus 6b by x raised to 4. And this is actually equal to k as shown in the slide. So at x is equal to x0, d square v by dx square becomes 8a. So the value of k is equal to 8a. And we know omega is equal to root of k by m. Substituting the value, we get omega equal to root of 8a. Question number 2. The acceleration due to gravity on the surface of Earth is approximately 2.6 times that of surface of Mars. Given the radius of Mars is about 1/2 the radius of Earth, the ratio of escape velocity on Earth to that of Mars is approximately. So here we should know two formulas. One is for kinetic energy half mv square and another is V, potential energy G mm by R equal to mgr. So escape velocity is that velocity in which the kinetic energy balances with the potential energy of attraction due to Earth. So half mv square is equal to mgr. So we get escape velocity V is equal to root of 2gr. So escape velocity for Earth VE is equal to root of 2GRE, and escape velocity for Mars VM is equal to root of 2GMRM. So VE by VM, that ratio becomes root of GRE by GMRM. So answer is root of 5.2 to 0.3. Question number 3 is a typical problem that is discussed in classical mechanics classes. A simple pendulum consists of two masses m attached by strings of length L are shown in the figure. The kinetic energy of the pendulum is, so answer is B. We find kinetic energy T is equal to half mv square. Since there are two masses, that is half m v1 square plus half m v2 square. The position coordinate of m x1 is equal to L sin theta, y1 is equal to L cos theta. And position x2 is equal to L sin theta plus sin theta 1 plus L sin theta 2, while y1 is equal to L sin cos theta 1 plus L cos theta 2. So substituting, we get v1 square is equal to L square theta 1 dot square and v2 square is equal to L square theta 1 dot square plus L2 theta 2 dot square plus 2 L square theta 1 dot theta 2 dot cos theta 1 minus theta 2. So kinetic energy T is equal to half into m into L square into 2 theta 1 dot square plus theta 2 dot square plus 2 theta 1 dot theta 2 dot cos theta 1 minus cos theta 2. So answer is B. Question number 4. The potential of a diatomic molecule as a function of distance r between atoms is given by V of r is equal to minus a by r raised to 6 plus b by r raised to 12. The value of potential at equilibrium separation between the atoms is, so similarly we find what we have done in problem number 1. We find dV by dr. and it will be equal to 0 at r is equal to r0. So r0 is found to be 2b by a raised to 1 by 6. Now the potential at equilibrium position is v at r equal to r0. So substituting that value, we get the potential at equilibrium equal to minus a square by 4b. Question number 5. A particle of mass m moves inside a bowl. If the surface of the bowl is given by the equation z is equal to 1 by 2 a into x square plus y square, where a is a constant, comma, the Lagrange of the particle is. So here there is a constraint, that is z is equal to 1 by 2 a into x square plus y square. So that reduces the degrees of freedom by 1. Now we should find an equation for Lagrangian in terms of r, phi and z. So kinetic energy is equal to half mv square. So we substitute v square in terms of cylindrical coordinates as t is equal to half into m into r dot square plus r square phi dot square plus z dot square. Now we have to replace all the values of z as well as z dot with respect to r or phi. So we get z dot is equal to ar r dot and z dot square is equal to a square r dot square, and potential is mgh or equal to mgz. So substituting for z equal to 1 by 2 a r square, we get potential is equal to v equal to mg into half into a into r square. So Lagrangian is equal to m by 2 into 1 plus a square r square into r dot square plus r square phi dot square minus g a r square. Now question number 6. 3 particles of mass m are connected by 2 identical massless springs of stiffness constant k. If x1, x2, x3 are horizontal displacement of mass from their equilibrium position, the potential energy of the system is. So let us consider x1, x2, x3 as the displacement of the 3 masses. Now in the case of a spring, the potential energy is found by the formula v is equal to half kx square. Here there are 2 springs, so v equal to v1 plus v2, and the displacement for v1 is x2 minus x1, while displacement for spring number 2 is x3 minus x1. So substituting those values, we get v equal to k by 2 into x1 square plus 2x2 square plus x3 square minus 2x2 into x1 plus x3. Question number 7. The Lagrangian of a particle of mass m moving in one dimension is given by L equal to half m x dot square minus bx, where b is a positive quantity. You are asked to find x. So since Lagrangian is given, we can find equation of motion by Lagrange's equation of motion, and we get mx double dot plus b equal to 0. Integrating x 2 times, we get x is equal to minus b by m t square by 2 plus c1t plus c2. Question number 8. A pendulum consists of a ring of mass m and radius r subtended by a massless rigid rod of length L attached to the ring. When the pendulum oscillates in the plane of the ring, the time period of oscillation is. So I have tried to visualize the figure for the compound pendulum. It's look like what is shown in the slide. The moment of inertia of ring is mr square. We have to find the moment of inertia of the compound pendulum. So using parallel axis theorem, we get moment of inertia of ring plus m into d square. So we get mr square plus m into r plus l whole square. Lagrangian of a compound pendulum is half I into theta dot square minus mgh, and it is clear that height is r plus l cos theta. Substituting those values in equation of motion according to Lagrangian, I theta double dot plus mg r plus l sin theta equal to 0, and if theta is small, theta double dot plus mg r plus l by I into theta equal to 0, and this is omega square mg r by l r plus l by r. So omega is equal to root of G into R plus L divided by 2R square plus L square plus 2RL. So time period is 2 pi by omega, and hence time period is 2 pi into root of 2R square plus L square plus 2RL by G into R plus L. Question number 9. Consider a particle of mass m attached to two identical springs, each of length L and spring constant K. The equilibrium configuration is the one where the springs are unstretched. There are no external forces on the system. If the displacement is small and that along is in x-axis, which of the following describes the equation of motion? Now, in order to find Lagrangian, we should know the formula L equal to T minus V, and T is always half mv square and V is mgh in the case of gravity, but here there is spring. So V is equal to half kx square. That is the formula we have to use. Now I have redrawn the diagram, and it is very clear that the elongation for the first spring is x square plus L square whole square minus, that is root minus L, that is by Pythagoras theorem. So similar is the elongation for the second spring also, that is root of x square plus y L square minus L. So substituting these values, we get potential is equal to k by 2 into x square plus L square raised to half minus L whole square plus k by 2 into x square plus L square raised to half minus L whole square. Now to solve this problem, we have to actually go for the binomial expansion because x is small. So rearranging according to the binomial expansion, we get V is equal to k L square into 1 plus x square by 2L square minus 1 by 8 into x raised to 4 by L square, etc. minus 1 whole square. And it is very clear that we have only taken the second order expansion of binomial, which is just sufficient to explain the result. So potential is actually V equal to k x raised to 4 by 4L square. Substituting this value in Lagrangian and finding Lagrange's equation of motion, we get mx double dot plus k x cube by L square equal to 0. Now coming to question number 10, this is a similar question what we have seen in question number 1. A particle of mass m is moving in the potential V of x is equal to minus half ax square plus 1 by 4 bx raised to 4, where a and b are positive constants. The frequency, that is a question asked at the stable equilibrium position. So again we remember those 2 points, that is dv by dx is equal to 0 at equilibrium point and d square v by dx square is equal to k. Finding dv by dx, we get minus a x plus b x cube equal to, and substituting x is equal to x0, we get it as 0. So x0 is equal to root of a by b, and finding k, we get k equal to minus a plus 3b x square. Substituting x is equal to x0, we get k is equal to 2a, and since mass is m, omega is equal to root of k by m, so omega equal to root of 2a by m. So let me conclude by a quote by Feynman. He says that I am always looking like a child for wonders I know I am going to find. Maybe not every time, but every once in a while. Thank you.